Hello, this is Module 6 of Introduction to Finite Elements. In this module, we'll work on the development and implementation of the Galerkin finite element method to the solution of time-dependent problems. Up to now, we have been working with boundary value problems in one or more than one dimension. Essentially, we pose a differential equation, ordinary in the case of unidimensional problems, and a partial differential equation in the case of multidimensional ones. We state boundary conditions, apply the variational principle, the Galerkin idea, and then we manage to obtain a system of linear algebraic equations from which the Galerkin approximation is obtained. In the case of time-dependent problems, we have now the presence of a time derivative term in the governing equations, representing the effect of the cumulative effect of what happens in the system. There are two main types of problems that we will focus on. One is the parabolic type problem, and the other one is the hyperbolic problem. Parabolic problem, a best example perhaps, is heat conduction in solids, and the hyperbolic problem is the problem of wave propagation. We'll see that the essential process is very similar to what we have done to now. You introduce a new function v, multiply the entire equation, all the terms in the equation by that function, and then integrate it over the domain. The term involving the highest order derivatives is manipulated by integration by parts or using Green's theorem in the case of multidimensional systems. And special care is needed to deal with the time derivative term. And this is where all the attention is concentrated. Essentially, it boils down to the addition of an extra term into the equations that because of the need to follow what happens to the system over time, a sequence of time steps are introduced, and one ends up solving finite element-like equations at each time step in order to progress from one time step to the next. All this will be covered in this session.